In this nugget, you and I get to discuss DNS Concepts, which is the magic behind how a friendly name like Google.com can be translated into an IP address. Let's begin. I'd like you to imagine our user Bob sitting at his computer. He just powered it on. He's got an IP address courtesy of DHCP, Dynamic Host Configuration Protocol. He also knows about a default gateway that he can use. And he's also been given a DNS server. Now, the reason that DNS server is so critical for Bob's computer to be aware of is because when Bob goes to www.google.com, from an IP network perspective, no one knows what's going on. Because www.google.com is a name of a web server, and in order to get to that web server, we need to forward that traffic, or the routers need to forward that traffic to the right IP network. And that's where DNS comes into play. What would happen is Bob's computer, when he types in www.google.com, in the background, Bob's computer would make a DNS request. That's for Domain Name System. The acronym also could be used for Domain Name Server or Domain Name Service. In any event, his computer makes a DNS request, and that request is going out to a DNS server. And the request is going to say, "Dear Mr. DNS server, I need to get to www.google.com. Could you please tell me what the IP address is for google.com so I can send a packet to that server?" And the server, if it can reply, will go ahead and respond back to that client. In this case, that's Bob's computer, with the answer. Oh, that's at 70.20.30.x. I'm just making up those numbers for a moment. And as you can imagine, there's millions and millions and millions of names out there on the internet. How do we keep track of it all? Well, we don't just have one DNS server. There's thousands and thousands of DNS servers. And in the background, they're all working together for that name resolution. So if this server didn't know about the answer to google.com, it could go ahead and refer up to another DNS server to ask for that same information. So if this DNS server tells that DNS server, this one can cache it and then forward the information back to Bob. And that way, if this server has to answer that same question over and over and over again, it doesn't have to make a request every single time to another DNS server to learn that information. So a cache is a place where we can store, usually temporarily, information that we've received. So a DNS server may cache DNS information it learned from another server. And as that answer goes back to Bob's machine is also going to cache that information. And the benefit of that is that if Bob needs to go to that same destination over and over again, he doesn't have to continue making DNS requests over and over and over. So in this example, Bob's computer is a DNS client, and this server up here is a DNS server. And if we label these servers as server 1 and server 2, we could also say that server 1 was a client to server 2 because server 2 was providing the information that server 1 needed. And generally speaking, in a client-server model, the entity that's making the request is considered to be the client, and the entity that's providing the information is considered to be the server. Now, in life, one of the common respectful things to do is if somebody asks for an apple, you give them an apple. If they ask for an orange, you give them an orange. Well, in DNS, we can help accommodate that by having different record types inside of DNS. And although there are dozens and dozens and dozens of record types, there's 5 that I want to share with you right now. One is an A record. An A stands for an address record. And an A record is referring to a record for an IPv4 address. So for example, if Bob's computer is running IPv4 and he makes a request out to the DNS server and says, "Hey, I would like the A record for the server www.google.com," the server should respond back with an IPv4 address, which may look like 72.1.6.4 or some other IPv4 address that's being answered or returned to Bob the client. Now, another record type that's in DNS or can be in DNS is a quadruple A record type. And you might think, wow, that looks like it's 4 times as long as an A record. And you know what? It is. So an A record for an IPv4 address is 32 bits in length. And a bit is a single position that can either be on or off, like a light switch. So for now, you can think of it as 32 light switches long. And a quad A record with 4 A's is an IP version 6 address record. And IPv6 is 128 bits in length. So if Bob's computer had been running IPv6 and Bob's computer made a DNS request looking for the quad A record for www.google.com, the response back from the DNS server would be expected to be an IPv6 answer, which is 128 bits in length. Or rather, that's the length of an IPv6 address. Another very common record type inside of DNS is an MX record, which stands for Mail Exchange, spelled MAIL. And that type of record would be used, for example, by email servers, just trying to forward email messages to another email server in a different domain. The CNAME record stands for canonical name. And by using a CNAME, we can do an alias from one name to the other. So, for example, if we were searching for www.bubba.com, and there was a CNAME record there that said, oh, what you really want is www.bubba1.com, that would be an example of a CNAME record. Then, of course, Bob at this computer would continue the resolution of www.bubba-1.com to an IP address. And the last one I want to share with you here is a pointer record. And it's called a pointer record because it actually points to a name. Now, most of the time, we're using DNS to resolve a name, like www.cbtnuggets.com to an IP address. However, if we want to flip that, if we have an IP address and we start there and we say, what is the domain name associated with this IP address, that's when the pointer record is used. So we could say, for example, hey, this address of 8.8.8.8, what domain is that associated with? And the pointer record would point to a name, and that would be one of Google's servers. So when you see pointer records, think reverse lookups, having an IP address already and wanting to know the name behind it. In large organizations, it's very likely that companies are going to have their own internal domain name system server. So when DHCP addresses and options are handed out, such as which DNS server to use, the computers can be told to use the DNS server that's local to their company. Then the challenge is, how does our internal DNS server know about the rest of the world? So normally what we'll have is we'll have a service provider DNS server out here on the internet, and our local DNS server will work in conjunction with the internet service provider's DNS server. And that DNS server can then work with additional DNS servers as needed for resolution of everything on the internet that's in DNS. So Bob makes a request to this DNS server. If this DNS server doesn't know it, makes a request to another DNS server. That answer comes back to our local DNS server, and the local DNS server feeds the answer back to Bob regarding, hey, google.com is at this address. And it can keep that in the cache on that local DNS server so that future requests for a period of time can be answered locally from the server without making additional requests. Now, one of our challenges is this. If we have a couple of servers at our location, let's say they're web servers, and we're acme.com. And let's say these servers are being load balanced and we're calling them www.acme.com. Our intention is that when Jill out here on the internet types in www.acme.com, DNS is going to resolve that to an IP address that is reachable right here. So maybe www.acme.com goes to our load balancer device. Perhaps we have F5 or NetScaler that has that IP address associated with www.acme.com. And then our load balancer can then load balance between the two identical servers that are sitting on our DMZ. So working with a service provider, we'd have to first of all make sure we got the domain acme.com registered to us, and then we'd want to make sure there's an A record for www.acme.com inside of DNS. So just as an example, this was 23.1.2.5. When Jill does her DNS request to her DNS server, saying, what is the IP address of www.acme.com? The response back to Jill should be 23.1.2.5. And then Jill would forward her traffic to her default gateway. It would be routed up to this load balancer and then load balanced across those servers. So we can see that having a DNS entry that points to the IP address where our devices are is really helpful because people can use names instead of memorizing IP addresses. So what about this scenario? Let's say we have a user who's connected to the internet. Here's his home. So this is a home user. And for that connection to the internet, this home user could be using DSL or cable modem. And for the purpose of this discussion, let's say this user has been assigned a dynamically assigned IP address. Let's say that address is 42.1.3.9. So on the internet, that's where this house could be found, at this IP address. Well, the user at this home has installed a camera. And the reason he installed the camera is because he wanted to keep an eye on his dog while he was away. So for example, if he's at work, he wanted the ability to go ahead and connect to the camera over the internet and see his dog. Now to make that function, there may be a little bit of work that the user has to do here on their router and firewall to let the correct ports and correct traffic through. But the problem I want to address right now is this IP address. This IP address is dynamically assigned from the service provider. What if it changes? What if it changes from 42.1.3.9 to 42.1.3.11? And then when Bob's at work, he tries to connect to the old address and it's not working. He doesn't know why. And the reason is that the IP address has changed and he's not aware of it. So to help address that, what we have is a feature called dynamic DNS. And the reason it's called dynamic is because we can have a moving IP address still mapped to a single name. For example, and we'll go ahead and give this user a name, we'll say it's Bob. Bob could go out to a company, for example, DNS.com is one of them. And what Bob could do is he could register under that domain. So for example, maybe he gets dns.com/Bob's house. And then what he does is he configures his camera to report in. So it's got some dynamic DNS software that's been configured to report into DNS and to report its current IP address. And as it reports the IP address, it's going to be reporting based on the global address that the internet sees that camera as. So there's a little smoke and mirrors that go on there. But the concept is that DNS.com/Bob's house now knows that that should map to 42.1.3.11. So now Bob simply goes to that URL, and because it's been dynamically updated, it translates into the right address, so Bob can get resolution to go to that IP address. And if a week later it changes from .11 to .98, no problem, because the camera is sending the updates to DNS.com associated with Bob's house. That information is then dynamically updated in DNS, and Bob goes to the same URL and can get to the IP address that corresponds to his camera. And that's the gist behind dynamic DNS. It's an IP address that can move from time to time, but some entity behind that IP address is reporting up to the dynamic DNS server to keep it updated. In this nugget, we've taken a look at the world of DNS, Domain Name System, which is the magic by which a name, a common name, a friendly name, like google.com, can be resolved into an IP address. I'm glad that you joined me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.